Wow. All right. That's quite more than I was expecting. Okay, so I'm Thierry from Belgium, land of chocolates and waffles and beer. And I'm a pretty shy speaker and an introvert, so this is kind of horrible for me. Every time I'm in front of this, I feel miserable, and this time I was particularly feeling miserable because this is the hardest talk I've ever given. It's a different thing speaking about an experience report that you've lived versus speaking about Conway's law and all the literature that is around that. So yeah. Now, yeah, why do you keep doing this? Well, what can I say? I love having spoken, something like that. All right. So that's all what you need to know about me. And let's go. Right. So, in 1968, Melvin Conway formulated this hypothesis that became Conway's law. Any organization that designs a system is constrained to produce a design that is a copy of the communication structures of that organization. Now, I want to thank Dawn Ahukana, who mentioned this graphic last night, and so I was able to add it. Thank you. Now, when Melvin Conway mentions a system, he really means this in the very broad sense. So this is not limited to software or IT systems. So this might be cars, this might be aircrafts, this might be factory machines, or engines, or telecommunication systems, or public transportation systems. So really anything. And interestingly, around the same time, different people from different communities made a similar observation that later became the mirroring principle. Now, it's not very clear if all of those people were aware of each other and that they were aware that they've made the same observation. And this was mainly concentrated around two communities. So we had the community of organization design and organizations as complex systems, where the focus is on designing organizations in such a way that tasks can be completed efficiently. And there we have, in 1967, Thomson, and in 1974, Galbraith. Now, when I was reading Thomson, I realized that, well, actually, Thomson was quite foundational for organization design. Because before Thomson, there were two lines of thought. There were the people saying, well, organizations are closed systems. And then there were the people saying, no, organizations are open systems. Now, organizations as closed systems assumes that all elements and processes of interest are internal to the organization. And so the idea here is to limit uncertainty. And so we want to limit the influence of the surrounding environment in which the organization functions. So think Taylorism. Think finding the one best way to execute a task. Whereas organizations as open systems, well, we cannot think of the organization without thinking of its surrounding environment. So the organization structure and behavior are affected by the influences of the environment. And so the organization, well, should be an adaptive system that tries to survive the environment it is running in. So Thomson said, well, it's not either or, no, it's actually both. An organization is both closed and open. So the internal technical system, the production component of the organization, should be closed. because we want to shield it off from the influences of the environment. But at the boundaries of the organization, well, the organization should attend and adapt to the changes of the environment. And so it should be open to the signals that come from the environment. And so therefore, it should be an open system at the boundaries of the organization. And then we have Galbraith that introduces the following proposition. The greater the uncertainty of a task, the more information decision makers need to process during the execution of the task in order to achieve a certain level of performance. Now, if the task is well understood before executing the task, well, much of the activity can be pre-planned. However, in the other case, if the task is not well understood, well, much more knowledge needs to be acquired during the execution of the task. Now, this sounds a bit similar like the simple and complex domain from Conway. Now, the effect of this uncertainty is that it limits us to pre-plan. And so, variations in organizational forms are actually variations in strategies that the organization uses to increase its ability to pre-plan, and so increase its ability to manage uncertainty. Therefore, executing a task is an organization design problem. And to solve this problem, Galbraith suggests 4 strategies that from a far distance somehow shows similarities with team topologies. Right. And then we have the people around product design and products as complex systems. And there we have in 1964 Alexander and in 1972 Pauw. Now, unfortunately, I wasn't able to read Alexander yet. Well, it's another book, and well, it's a different thing reading a book or reading a paper in volume of work. But yeah, there I will follow the advice that James Bloom gave last year at Domain-Driven Design to Trond and Joan. You can't read all the books. Start writing. It's a bit what I've done. But Pauw is interesting because, well, Pauw, so his paper on the criteria to be used in decomposing systems into modules is like the #1 paper in a list of top 10 papers anyone in the software industry should read. And Pauw introduces the concept of information hiding to manage complexity or to tackle complexity. And so every technical module from a technical system is informationally isolated from each other, allowing different teams to work independently from each other on different modules. And this information hiding principle is, well, a fundamental principle underlying the mirroring principle. Now, both organization design community and product design community take their inspiration from Simon, the architecture of complex systems, where Simon introduces the idea of partitioning complex problems or partitioning complex systems into a series of linked sub-problems or linked subsystems that allows us to better understand or better solve complex problems or better understand complex systems. So, in the end, well, we can express the mirroring principles in terms of structural correspondence between 2 networks, a technical network and an organizational network. And so there will be a mapping from a technical module towards a design team. Now, all of this has been summarized in a 2016 paper called The Mirroring Hypothesis by Baldwin. And it's actually a very interesting read. It's a long paper, it's 20 pages. But, well, it shows you all the variations of the mirroring principle in different industries. And then it goes with a truckload of references, which I've only touched like a really small part here. And so their conclusion is the organizational ties in firms will correspond to the technical dependencies of the work being performed inside the organization. Now, in recent years, this mirroring principle and Conway's law has resurfaced as a kind of guiding principle on how to organize teams and design structures of organizations. Although there are still quite a lot of people that are rather skeptical about this because, well, it's just an hypothesis. Now, there is a little story behind Melvin Conway's paper that he explains on his website. So he first sent his paper to Harvard Business Review, where it was rejected on the ground that, well, there is no proof for the thesis. And so he sent it to Datamation, which was a major IT magazine back in the days, and they then eventually published it in April 1968. But by now, there has been quite some academic research that supports the thesis. And the first one is in 2004 by Souza and friends, where they looked at the design process of a commercial aircraft jet engine at Pratt & Whitney. And so they looked at the organizational problems that exist at the boundaries of the system components inside the jet engine. So meaning whether there is a misalignment between the design team boundaries and the interfaces of system components. And their conclusion was that, well, we can provide empirical evidence that product ambiguity exists, and it is most likely to exist across organizational and system boundaries. So meaning there is a great likelihood that some of those component interfaces of this jet engine are not covered by design team interactions, which can lead to major setbacks involving significant rework that can cost a lot, like really extremely. And in the paper, they refer to two such major setbacks that happened during the design process of this jet engine. So what they are actually saying is that if there is a misalignment between the structure of the organization and the product architecture, well, there will be problems. Then in 2006, we have Cataldo and friends that explored the consequences of congruence for the speed and efficiency of software development work inside a single software project. So they investigated the impact of misalignment. And what they found was that tasks were completed more rapidly when the patterns of communication between team members were congruent with the patterns of interdependency between the components. So essentially saying that if the team is aligned with the components they are working on, they will be more efficient. In 2007, we have a study conducted by Gokpinar and friends where they looked at the design of cars in the automotive industry, and their conclusion was that while mismatches between product architecture and the structure of the organization are positively associated with quality problems. Again, what they are saying is, if there is a misalignment between the structure of the organization and the product architecture, well, there will be problems. And then lastly, we have in 2012, the first empirical evidence for the software industry, provided by research, again, by Baldwin and friends. And their finding was that software products, tend to mirror the structure of the organization in which they are being developed. And to prove this thesis, they compared open source software with closed source software on the grounds that the open source community is a loosely coupled organization by design because individual contributors have diverse goals, belong to different organizations, work in different geographical locations and in different time zones, and do not have formal authority about the development process. Whereas closed source organizations are tightly coupled organizations because they consist of smaller teams that are co-located, having common shared goals where people are most of the time allocated full time to the project and where they do have formal decision-making authority about the design, about the development process. And so their approach was to compare the architecture of open source software and closed source software. And they compared software that had similar functionality and that were similar in code base size. And so they identified 5 categories of software: financial management software, word processors, spreadsheets, operating systems, and databases. Now, obviously, commercial firms are a bit reluctant to share their code base, especially for research that will compare their code base with the free versions. Well, yeah. Duh. And so, sometimes, well, they didn't have a closed source code base, and so, well, in those cases, well, they fall back on software that started as closed source, but that eventually, at some point, was open sourced. And then they took the code base of the very first release of the open source version, and they compared those. Now, in this research, they essentially explored whether organizations with distinctly different forms will produce products with distinctly different architectures. And in the end, well, they found out that loosely coupled organizations like open source tend to produce products that are that have a more modular architecture than tightly coupled organizations like commercial firms, which somehow confirms Parnas's information hiding, which allows individual contributors to work independently from each other. All right. Now, over the decades, many different people have reformulated Conway's law in various different ways. And every paraphrase, well, comes with new insights on the consequences and implications of the law. And sometimes, well, they seem to contradict each other. But in the end, they all come to the same conclusion. Now, this was pretty confusing when preparing this talk, and didn't really help to come with a compelling story. And each time I'm practicing this or giving this presentation, I feel an idiot because I'm constantly contradicting myself. So essentially what is going to happen now is I will say A, then I will say B, then I will say, well, actually, no, it's A. And, well, sometimes it's also B. Oh, and then we'll add C to add some more confusion. And in the end, it will be, well, it's actually none of all of this and all of A, B, and C. Right? Okay. It's going to be fun. So, in 1979, somewhere 10 years after Conway's paper, Jordan and Constantine rephrased the law more firmly by saying the system is isomorphic to the organization. And isomorphic means it is corresponding or similar in form and relations, being the same or similar in structure or shape or form. So this pushes the idea that any system that will be produced by an organization will be shaped according to the structure of the organization. So essentially this means the organization drives the system design. Now this has an interesting consequence. If you have two subsystems that are designed by two distinct, different design teams, and those design teams do not communicate with each other, well, by definition, those two subsystems will not communicate with each other. Haha. But there is more. There's also a mathematical definition of isomorphism. It is a structure-preserving mapping between two structures, or it is a one-to-one correspondence between two structures. Now, this is interesting because this indicates that we cannot ever have an organization where two or more components from our system correspond to a single unit, a single team of our organization because of this one-to-one mapping. And so this implies that no single team can be responsible for more than one service. Now, this is quite a strong formulation of Conway's law, way stronger than how Conway itself formulated the law, because Conway speaks about homomorphism in his paper. And homomorphism is a more relaxed version of isomorphism. It is a structure-preserving mapping, but it is not a one-to-one relation. And this is what makes Conway's law. It is this homomorphic force. It is this power of one system, one structure, to bring itself about onto another system or another structure. So the force creates the same structure for organization and system, and then it preserves the structure. So it maintains the structure. This means that if we have 4 teams maintaining a compiler, well, we will have a 4-pass compiler. But over time, this 4-pass compiler will reassert itself onto the organization. And so the organization cannot have one team anymore to maintain the compiler. It needs those 4 teams. And this is why COBOL organizations find it very difficult to do anything approaching agile, because the organization is in harmony with the software. The organization created the software, but over time the software imposes a structure on the organization. And if we try to change the organization, well, the system won't let this happen. It will work back. Now, because this is not a one-to-one mapping, a homomorphism from an organization towards its system does not require that every part of the organization, every team of the organization is mapped on a single component of the system. And so this means that a single team can be responsible for 2 or more services. All right. Then we have Raymond, Eric Raymond, from the seminal essay, The Cathedral and the Bazaar. Anyone has read The Cathedral and the Bazaar? Right. So, in The Cathedral and the Bazaar, Raymond compares open source software with closed source software. And so he argues what Baldwin confirmed in her research when comparing open source software with closed source software, that open source software is inherently more modular than closed source software. So now in 1996, Raymond, rephrased the law by saying the organization and the system are congruent. And so congruent means in agreement, in harmony, identical in form, exactly equal in shape and size. So this reinforces this homomorphic force, this structure-preserving mapping between the structure of the organization and the structure of the system. And Conway, exemplifies this homomorphic force in his paper using the COBOL and ALGOL compiler example. So a contract research organization consisting of 8 people is tasked to design a COBOL and ALGOL compiler. So after some initial estimations on complexities and difficulties and timings, they decide to assign 5 people to the COBOL compiler and 3 people to the ALGOL compiler. And the result is that the COBOL compiler runs in 5 passes and the ALGOL compiler runs in 3 passes, obviously. Now, the bigger the organization is, the less flexibility the organization shows. And so the more pronounced the effects are of this homomorphic force. Now, the effects of this homomorphic force can also be expressed differently. And so Jordan and Constantine mentions this story in their book of an engineer that was tasked to design a program for a 12-bit microcomputer. And so he estimated the work to be 6 months. But his manager found this unacceptable, way too long. So he decided to add an extra engineer in the hope to speed up work, obviously. Upon which the original engineer reacted by saying, yeah, but 2 engineers won't fit in there. And so if we assign 1,000 engineers to design a system before a formal design happened, chances are we will end up with at least 1,000 modules, because 2 engineers won't fit in a single module. Now, this is just another expression of Mealy's law, which relates to the mythical man-month, and Brooks' law, adding more people to a late project will make it even more late. So it's lovely how all of these things are interconnected. Right. And then in 2004, we have Coplin and Harrison, who rephrased the law by saying the organization must be compatible with the system. And compatible means able to exist together without conflict, without problems. Now, this is interesting. So we have Jordan and Constantine that say the system must be isomorphic to the organization, essentially saying it is the organization that drives the system design. And here we have Coplin and Harrison that are saying exactly the opposite. Well, it is more likely that the system drives the design of the structure of the organization. And if they are not in harmony, well, the system will impose a structure on the organization to have the organization again aligned with the system. Whereas we have Raymond that stays in the middle, like, oh yes, organization and system are congruent. They are in agreement, in harmony, exactly equal in shape and form and in size. But wait, this contradiction between Jordan and Constantine on the one hand and Coplin and Harrison on the other hand can also be interpreted differently. At the start, at the start, the organization imposes a structure on the system. So the organization acts as a force on the initial system design, the greenfield design for the system. So the structure of the organization defines the possible system designs we have at our disposal. And this is exactly what Conway also says at the start of his paper. The very act of organizing means that some design decisions have already been taken. But over time, when the system grows, the system design matures, the system becomes long-lived and gains expressions in couplings that constrain. It is now the system design that acts as a force on the organization. And this closes the option space we have for designing the structure of our organization. And so this brings us to the reverse Conway's law. In long-running organizations, having long-running systems, it is the system that imposes a structure on the organization. And this is what we see with COBOL organizations. If we have 3 teams, if we have a three-tier system consisting of a front end, a back end, and a database, chances are we will find in the organization a front end team, a back end team, and a database team. So the system mirrors itself back on the organization. So we see this happening with long-living organizations having long-living systems. So this might be a bit more expensive, and it might be not the most efficient way of working, but hey, it's working, and that is fine, as long as it allows us to continue. Now, where problems start is when management decides to reorganize, and they decide to send one layer of the system to another country. Or they decide, oh, we don't need the database team anymore. Well, the database is done, isn't it? And so they start reorganizing the organization in such a way that the organization is not compatible anymore with the system, but the system won't allow that. The system will work back, and it will reassert itself on the organization. And this is where Matthias Ferraz quotes one CTO who told, yeah, well, we reorganized, but it seems the system didn't get the memo. Yeah. So this is what happens with long-lived systems. We cannot just reorganize, because we have this homomorphic force, this structure-preserving mapping between the structure of the system and the structure of the organization. The force creates the same structure, but the force also maintains this structure. And so over time, the system will reassert itself on the organization, and so both sides are going to push on each other. And this is where the inverse Conway's maneuver falls short. Or more precisely, that people have the wrong expectations about the possibilities of the inverse Conway's maneuver. Oh yeah, well, we just have to reorganize and that will solve all of our technical problems. Right. Well, no. This won't happen. This is simply not true, especially not for rigid, long-lived systems, because of this inverse Conway's law. System design acts as a force onto the organization. And this obviously brings us to the inverse Conway's maneuver, who was introduced in 2010 by folks from ThoughtWorks, Johnny Leroy and Matt Simons. So before organizing teams and before designing the structure of an organization, well, we need to understand which architecture we want to achieve for our software system. And so it all starts from the system architecture, which pretty much, well, repeats Copeland and Harrison. The organization must be compatible with the system. And so the system architecture drives the structure of the organization to ensure that the organization stays compatible with the system. Now, this works for flexible systems and for greenfield systems, because the structure of the organization defines the system designs we have at our disposal. However, this doesn't work for rigid, long-lived systems because of the reverse Conway's law. As system design matures, the system becomes long-lived, becomes rigid, gains expressions and couplings that constrains. It is now the system design that acts as a force on the organization, and so this limits the possible structures we can use for designing our organization. But having said all of that, clearly, for flexible systems and for greenfield systems, well, we should architect the organization to architect the system, repeating Jordan and Constantine. The system is isomorphic to the organization, and so the organization creates the software design. But this means two things. If we want separate modules, well, we need to separate teams. If we have two distinct pieces of functionality, well, we should split the team into two distinct teams, working on two different modules, and each team can optimize around their module, essentially repeating Parnas's information hiding, which allows distinct teams to work independently from each other on different modules. Now, conversely, if we ram two teams together, well, we will find that their modules and the functionalities become intertwined, which confirms the research from Baldwin when she compared open source software with closed source software. Second, collective code ownership leads to more integrated teams and code. Now, this might be a good thing, this might be a bad thing. If we want to separate code because we have distinct pieces of functionality, well, yes, we need to separate teams. But if we have lots and lots of layers and lots of superfluous objects, we might be better off to bring the code together and bring the people together, and this will reflect itself in the software design. But the inverse is also true. So drafting the system architecture is already designing the structure of the organization. Again, confirming Copeland and Harrison, the organization must be compatible with the system. And this is exactly what the inverse Conway's maneuver is all about. Now, as we all know, the initial design of a system is rarely the best. So as we work on our system, while we learn the relevant architecture. As we move forward, while we get new information, we get new feedback, and we learn and we adapt. But this has consequences for the organization. So this requires organizational flexibility in order to come to an effective system design. If we don't have organizational flexibility, well, we are constrained to produce a system design that is a copy of the real on-the-ground communication structures of the organization. Now, be aware the real underground communication structures of the organization are not necessarily the ones depicted on the traditional organization chart. So people do not limit their communication to the lines of the org chart. No, teams will reach out to whomever they depend on to get the work done. Similarly, incremental software design also has consequences. As the system grows, software grows. As software grows, entropy grows. To contain entropy, we need to refactor. Many refactorings lead to significant redesigns. So as a result, incremental software development will impact the organization because we are changing the design of our system. We are redesigning the system. And so this requires growing and redesigning the organization together with the system, so to make sure that both stay aligned. So this requires, again, organizational flexibility. So the organization and the system need to co-evolve. And Adrian Cockcroft, so the former chief architect of Netflix, which led Netflix from going from a DVD renting company to a video streaming company. So he confirmed this in a Mastodon conversation with Ruth Mellon, where he shared, I think I have seen this at Netflix and at AWS. On an annual basis, teams were realigned with the new domain boundaries. But this creates two imperatives. To keep asking ourselves, is there a better design not available to us because of the organization? And can we change the organization if a better design is found? And Melvin Conway, made a similar observation 50 years later. The importance of the law is not so much that we are constrained to produce a design that is a copy of the communication structures of the organization. Now, the importance of the law is that the organization is keeping us from designing the things we should be building to delight our customers. And if the organization is preventing us from building the right thing, the organization should be flexible enough to allow us to redesign the organization in order to find a more effective system design to better fit the needs of our users. Again, this requires organizational flexibility, which is not that easy because that doesn't necessarily work for long-lived, rigid systems because, again, the reverse Conway's law. The system design acts as a force on the organization and limits our options for designing the structure of our organization. Because the initial design is rarely the best, and because of incremental software development, system architecture is never really done. It's never really finished. It's something that is continuously ongoing. Therefore, a system architecture is a great source for archaeological research on past historical enterprise decisions. Because, changes we are making now need to coexist with changes that we've made last year and changes that we've done the year before. And once we adopt this perspective, we stop trying to rip apart our systems and start all over again. No, from now on, we start to focus more on incremental change. And so here starts the history of our changes. Now, 2 weeks ago at Newcrafts, I was asked, can you give us an example of this archaeological research and relation of past decisions with current code base? So I can give you two. So in our platform, we have functionality that resembles Dropbox or Google Drive, so files can be uploaded. That used to be called a digital vault, because the idea was that confidential documents could be uploaded and they were secured in this environment. But nobody was using the term digital vault. Product managers were speaking about file managers, and they were speaking about file manager with the customers, and so the customers start speaking about file managers. But we were still there with digital vault in our code. And still today, we have this one single folder called digital vault about some infrastructure. Why don't you rename it? yeah, well, it doesn't seem important enough. And yeah, well, the other thing is, yeah, well, we need to open a pull request, explain why we renamed this, blah, 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 lots of administration that you don't want to do. The other thing was that in our many cloud provider migrations, which is a story on its own, we eventually ended with the current cloud provider, and I made the mistake of creating all the environments in a single account. And obviously, to segregate the environments, what do? Well, you add prefixes or suffixes with environment names. Yeah. Well, this was solved. We went from single account to multi-account, but we still have those environment names in the infrastructure resource names. And so that's, each time a new member enters in the team, you're like explaining, yeah, well, so this is because, well, this thing in the past. This is a bit more difficult to rename. Well, especially the database. It's like tearing down database, getting it up again. Whatever. One day it will get solved. All right, now, because of those past historical decisions and history of changes, well, software development efforts that lead to large, long-running, rigid legacy systems create system structures that are not necessarily congruent, not necessarily in harmony with the structure of the organization at present, like today, now, because reorganizations of people happen far more frequently than reorganizations and redesigns of systems. And so the state of the system does not reflect the structure of the organization, and also it doesn't reflect all the past decisions of the organization and the flow of people through the organization. And so this adds a time component to Conway's law. Now, to understand this, well, we need to go through software engineer half-life and the effect of this on turnover and on code bases. So, software engineer half-life is in fact the residency time of a software engineer on a code base, like the time they spend working on a single code base. And it seems that the industry average is 3.2 years. So engineers spend on average 3.2 years working on a code base, and then they move on and they work on another code base. So this means that for a team of 10 engineers, half of the team has left the team over the next 3.2 years. If we want to keep the team constant, well, we need to replace those engineers. But there is no guarantee that the replacement has a similar productivity. Might be that a low productive engineer is replaced by a high productive engineer. High productive engineer might be replaced by a low productive engineer. So for small teams, this can significantly change team productivity. Ouch. Now, in the end, not all engineers are equal in productivity. Even the same engineer is sometimes more productive on one code base and less productive on another code base. Now, this is mostly related to code base sizes. So it's a different thing to add 100 lines to a 1,000 line code base than to add this to a 1 million lines of code base. Now, generally speaking, well, we can say that team productivity goes down when code base sizes increase. All right. Now, to see the effect of this software engineer half-life, well, we will run a turnover simulation on a team of 7 engineers that is working on a code base during 5 years. And during this simulation, well, we will use lines of code as a productivity metric. Yeah, I know. This is outrageous. How do you dare? Well, look, it's just for the case of the model, and I'm with you. Return on investment and value creation are way better metrics, but here is the thing. It's difficult to tie back to a single engineer. And so for simulations, it doesn't work. And in the simulation, every day there is a fixed probability that an engineer leaves the team and is replaced by another engineer with a random productivity. All right. So the result of the simulation is this graph, where from left to right we have time, So on the left, we have the start of this team of 7 engineers with 0 lines of code. And then from top to bottom, we have the contributions of every engineer. And so each color is a different engineer, and the bandwidth of one band shows the productivity of an engineer. Right, so at day 180, we have the first engineer, the purple engineer, that leaves the team. And this is shown by a vertical black bar. Now, the contribution of the engineer is static, so what they created before leaving still stays in the code base. So therefore, we keep the band, but with a lighter color, so light purple. Now, the purple engineer is replaced by a pink engineer that seems to be more productive, but they only stay 200 days. Right. Now, at the end of the 5 years, we find that the team of 7 engineers has churned through a grand total of 19 engineers, and that the majority of the code base has been written by people that are no longer in the team. Only 37% of the code base has been written by the people that are still in the team after 5 years. So, this means that the structure of the software reflects the structure of the organization integrated over time. So this means that, well, there is a time component to Conway's law. And large software systems, as we see them today, are actually a fossilized representation or fossilized footprint of past engineers. So this also means that anytime we release a new version of our product, we are actually shipping our organization together with its structure, together with all the past historical decisions we've made, and together with the flow of all the people that went through the organization and that have contributed to the code base. All right. So, if managers decide on engineering teams and decide on which services are being implemented by which teams, we have managers deciding on system design. And so managers are, in fact, architects. On the other hand, anyone that claims to be an architect, well, need both technical and social skills. They need to understand both the people and the work inside the socio-technical system. And so they need to have a say about the structure of the organization. Therefore, architects are managers too. So everyone who makes decisions about the shape and size and placement of engineering teams is strongly influencing system design. And so by now it should be clear that the structure of the organization and the architecture of our system are communicating vessels. And so we need to tackle both together at the same time by the same group of informed people, managers and architects. Now, to conclude, start small. Delay staffing for as long as possible, because once we start to add staff, we are adding new communication structures to our organization. We are adding new, we are adding more nodes to our hierarchy of the organization. So we are adding new nodes to our software, and so the software grows, and this will have an impact on the software design. So instead of that, well, we should start with the smallest team possible and get a small system working. Small teams, small systems. And then we grow the team with the system as we need. And that is the only way we can contain system architecture and system design. The bigger the team is, the more the structure of the organization influences or imposes a structure on the system design. So do not start to think big right from the start. Once we start to think big right from the start, well, we need to staff. Once we staff, systems grow out of control because of the 1,000 modules effect. And so, well, we need to keep the people working. Now, I know this is a hard sell to tell to managers, no, don't hire. Try to grow the business, not the teams. I remember when we concluded the second funding round for the FinTech, our CEO was like going crazy, like, oh, now we have the money. We need to hire. And I was like, whoa, no. Our system is not ready for this. So luckily they didn't hire. But I'm afraid it's not because I've said that they shouldn't hire, but because, well, it's difficult to find people. Yeah. But still, it's a hard sell for managers. And I was also asked at Newcraft, yeah, how do we sell that to managers? Well, I don't know. The only thing we can say is like, well, dear manager, we shouldn't hire because we have experience with that and we've seen it doesn't work. And well, in the end, somehow we have more experience than you. Yeah. All right. So start small. Probably slightly smaller than we think we need. Thank you.